Look up at the night sky. Your eyes deceive you. You see a serene tapestry of light, a quiet painting hung over the earth, but what you are actually witnessing is a theater of unparalleled violence. You are looking at a raging inferno. Scattered across the cosmos are trillions of thermonuclear furnaces, stars detonating with unimaginable fury, black holes tearing apart entire worlds and spitting out jets of plasma that cut through the darkness like cosmic blowtorches. The universe is quite literally on fire. Every second, our own sun converts 4 million tons of matter into pure energy, generating temperatures in its core that reach 15 million degrees. And our sun is just an average, unremarkable ember in a galaxy of hundreds of billions. Beyond our Milky Way, quasars burn so brightly, they make the concept of light itself seem blinding, radiating the energy of a trillion suns. The cosmos is packed with heat, with friction, with the violent birth and death of matter. So reason dictates that the universe should be a furnace. If you were to step outside the fragile atmospheric shell of our planet, you should step into an oven. Yet, the reality is a chilling paradox. If you floated into the void of deep space, away from the immediate embrace of a star, you would not burn. You would freeze. The ambient temperature of empty space hovers at a desolate 2.7 degrees above absolute zero. That is roughly negative 270 degrees Celsius. It is a cold so profound, so absolute, that atomic motion itself begins to shudder and stop. How is this possible? How can a universe overflowing with nuclear fires, filled with more energy than the human mind can mathematically comprehend, be fundamentally freezing? It is like standing in a sealed room packed with 1 billion blazing heaters, only to find the air itself is turning your blood to ice. The answer to this paradox reveals a terrifying truth about the architecture of reality, the nature of nothingness, and the ultimate inescapable fate that awaits everything we know. If you seek the truth in the dark, if you are drawn to the beautiful terror of the cosmos and the strict science that decodes it, subscribe and join us on this journey. We are going to dismantle the illusion of the night sky. We are going to explore the cruel thermodynamics of the void, tracing the heat from the heart of a dying star out into the merciless expanse where it simply vanishes. Because to understand why space is freezing, we first have to rigorously define the physical mechanics of empty space. To understand the profound hostility of the void, we must first strip away a fundamental biological bias. We are creatures born at the bottom of an ocean of gas. Every sensation of temperature you have ever experienced has been mediated by an invisible, suffocating blanket of nitrogen and oxygen. When you step outside on a winter morning and feel the biting cold, you are not actually feeling the temperature of the universe. You are feeling the atmosphere actively robbing you of your own thermal energy. The air molecules collide with your skin, draining the kinetic energy from your cells and carrying it away on the wind. Conversely, when you stand near a fire, the heated air rushes over you, violently transferring its frantic motion back into your flesh. You have spent your entire life in a thermal bath, a constant tactile exchange of energy with the matter pressing against your skin. Because of this, our brains are hardwired to misunderstand what temperature actually is. We intuitively view cold as a creeping, malicious presence, and heat as a physical substance that fills a room. This illusion is so powerful that for centuries, the greatest scientific minds on Earth believed exactly that. In the late 18th century, the prevailing scientific doctrine stated that heat was an invisible, weightless fluid called caloric. They believed that this ghostly liquid flowed naturally from hot objects into cold ones, much like water seeking a lower elevation. Antoine Lavoisier, the brilliant French chemist who mapped the architecture of combustion and respiration, actually listed caloric as a fundamental element of the universe, and it made perfect sense to the human eye. If you place a red-hot iron rod into a bucket of cold water, you can almost see the heat bleeding out, violently boiling the water until the two find a quiet equilibrium. It was a beautiful, elegant theory. It was also entirely wrong. The universe does not operate on elegance. It operates on brutal, microscopic chaos. The death of the caloric theory began in a dirty, deafening weapons arsenal in Munich, Germany, in the 1790s. A physicist and military engineer named Benjamin Thompson, later known as Count Rumford, was tasked with supervising the manufacturing of artillery. To make a brass cannon, workers had to bore a massive hole into a solid cylinder of metal using heavy, horse-drawn drill bits. The process generated an astonishing amount of friction. To prevent the drill from melting, the brass was submerged in a wooden box filled with water. As the horses marched in their endless circles, driving the blunt steel against the brass, the water would boil. It would boil continuously, violently for hours on end, as long as the horses kept moving. Rumford watched this with growing suspicion. According to the science of his time, the friction was squeezing the caloric fluid out of the brass, like water being wrung from a sponge. But Rumford noticed that the brass was not degrading. It was not losing mass or changing its chemical properties. The supply of heat seemed literally infinite, generated entirely by the mechanical labor of the horses. He realized a terrifying, paradigm-shifting truth. Heat was not a fluid. Heat was not a substance at all. Heat was motion. It was the frantic, invisible vibration of the atoms themselves. When the heavy steel drill bit tore into the brass, it physically agitated the metallic atoms, forcing them into a state of violent, microscopic panic. That panic was transferred to the water molecules, vibrating them so intensely that they shattered their liquid bonds and erupted into steam. Temperature, as we measure it, is nothing more than the average speed of atomic vibration. The faster the atoms tremble, the hotter the object. If you freeze an object down to absolute zero, you're not filling it with a substance called cold. You are simply draining away all its kinetic energy until the atoms themselves shudder to a complete and perfect halt. This historical revelation is the absolute key to unlocking the paradox of the freezing cosmos. If heat is purely the physical vibration of matter, what happens when you remove the matter? Space is a vacuum. It is not a perfect vacuum, but it is an emptiness so profound that our earthly physics become crippled. In the vast dark stretches between galaxies, you might find a single atom of hydrogen drifting in a volume of space the size of a large house. There is no crowd of molecules to bump into. There is no air to hold the warmth, no atmospheric ocean to carry the kinetic panic from one place to another. Imagine a massive, ancient cathedral bell suspended in the center of a dead, empty city. If you strike that bell with a heavy iron hammer, the metal will deform, the atoms will vibrate in intense agony. On Earth, that vibration pushes against the air, creating a shockwave of sound that travels for miles. But if you place that same bell in a total vacuum and strike it, the metal will still vibrate. The energy is there. But without the air to carry the wave, the bell screams in absolute silence. The kinetic energy is trapped within the object. Heat in the cosmos operates exactly like that silent bell. On Earth, we rely on three mechanisms to move heat: conduction, convection, and radiation. Conduction is the direct physical touch, the burn you get from touching a hot stove. Convection is the circulation of a fluid, the rising of hot air or the boiling currents in a pot of water. But in the vacuum of space, conduction and convection are amputated. They require a medium. They require an ocean of atoms. The universe is left with only one language to communicate its fury: radiation. Stars do not warm the vacuum of space. They cannot. Instead, they vomit their immense thermal energy outward in the form of electromagnetic radiation. They fire invisible, massless projectiles, photons of infrared, visible light, ultraviolet, and X-rays, screaming through the dark at 300,000 kilometers per second. This light carries the energy of the stellar furnace, but it does not heat the empty space it travels through. It is pure potential. Like an unread letter carrying a devastating message, the photon holds its energy intact, traveling for perhaps 10 billion years across the silent abyss. It will only deliver its heat when it finally crashes into something solid: a rogue asteroid, a dead moon, or the hull of a spacecraft. This creates a terrifying reality for any physical object venturing into the void. Because space itself has no temperature to offer, your thermal fate is entirely dictated by geometry and line of sight. It is a brutal, binary toggle between the fire and the dark. If you were to float in Earth's orbit, perfectly exposed to the unshielded light of the sun, you would not freeze. You would bake. Without an atmosphere to scatter and absorb the harsh ultraviolet and infrared barrage, the side of your body facing the star would rapidly absorb the incoming photons. The atoms in your spacesuit and the skin beneath it would be forced into a violent kinetic frenzy. The temperature on the sunward side would soar past 120 degrees Celsius. Water boils at 100 degrees, but the geometry of the void is merciless. The side of your body facing the infinite empty dark receives almost no incoming photons, and because you are an object made of vibrating atoms, you are also radiating your own heat away into the blackness as infrared light. You are bleeding your thermal energy into the bottomless sink of the universe, and there is no air wrapping around you to trap it. Consequently, the shadowed side of your body would plummet into the negative 150-degree range. You would be simultaneously burning and freezing, torn apart by a thermal gradient that human biology was never designed to endure. The mathematics that govern this violent exchange were formalized by physicists Josef Stefan and Ludwig Boltzmann. They uncovered a mathematical law that describes exactly how an object radiates its heat into the dark. The mathematics reveal a merciless truth. The energy an object bleeds into space is proportional to the fourth power of its temperature. This means that if a star or a planet is just twice as hot, it does not radiate twice as much energy into the void. It violently purges 16 times as much energy. The hotter an object is, the more frantically it throws its heat away, desperately trying to reach an equilibrium with the surrounding emptiness. But because the emptiness is practically infinite, that equilibrium is a death sentence. The object will continue to hemorrhage its heat, photon by photon, until it matches the desolate baseline of the universe. And what exactly is that baseline? If space is truly empty, and emptiness has no atoms to vibrate, how can scientists state with absolute precision that the ambient temperature of deep space is 2.7 degrees above absolute zero? To understand this, we must look to an accidental discovery made in 1964, a discovery that forced humanity to listen to the ghost of its own creation. In Holmdel, New Jersey, two radio astronomers named Arno Penzias and Robert Wilson were operating a massive, ultra-sensitive piece of equipment known as the Holmdel horn antenna. It looked less like a telescope and more like a colossal metallic ear scooped out of the Earth, designed to bounce microwave signals off early satellite balloons. To ensure they could hear the faintest whispers from orbit, Penzias and Wilson cooled their receiver with liquid helium, driving its internal temperature down near absolute zero to silence the thermal noise of the metal itself. But no matter where they pointed the giant horn in the sky, they heard a sound. It was a low, persistent microwave hiss. It was present during the day. It was present at night. It did not change when they aimed at the blazing heart of the Milky Way, and it did not change when they aimed at the darkest, emptiest patches of intergalactic space. It was a uniform static, coming from everywhere at once. They checked their wiring. They dismantled the receiver. They even climbed into the throat of the antenna and scrubbed out a layer of pigeon droppings, desperate to find an earthly explanation for the noise. The static remained. The mathematics of the signal revealed that this microwave hum possessed the exact thermal signature of an object resting at negative 270 degrees Celsius, 2.7 degrees above absolute zero. They had not found a flaw in their machine. They had found the edge of time. Penzias and Wilson had detected the cosmic microwave background. They were listening to the fading, stretched-out echo of the Big Bang itself. 13.8 billion years ago, the universe was not an empty void. It was a compressed, infinitely dense, blindingly hot plasma. As space expanded, it stretched that primordial fire. The intense, high-energy gamma rays from the dawn of creation were pulled and elongated by the expanding fabric of the cosmos over billions of years, stretching until they cooled into the faint, weak microwaves washing over the Holmdel antenna. When astrophysicists say space is freezing, they are not talking about the temperature of nothingness. They are talking about the temperature of this ancient, dying light. It is the absolute floor of reality. If you take a rock, place it in the deepest, darkest void between the galactic clusters, far away from the light of any living star, it will slowly bleed its heat away. It will cool down for millions of years until its atomic vibrations match the faint, ghostly warmth of the Big Bang's dying breath. And there it will sit, trembling at 2.7 degrees, waiting for the end of time. The terror of the cosmos is not just that it is cold, it is the realization of the scale. The stars and quasars are localized anomalies, brilliant but pathetically isolated bonfires burning in a desert of unimaginable proportions. If our sun were reduced to the size of a single grain of sand, the nearest star, Proxima Centauri, would be another grain of sand nearly 30 kilometers away. Between those two grains of sand is not just empty distance. It is an active, hungry abyss. The heat from the fires is desperately trying to fill the void, but the void is mathematically unwinnable. To grasp the true scale of this thermodynamic symmetry, we must confront the ratio of fire to ice. When we look through the lenses of our most powerful observatories, we see a universe that appears crowded with glowing matter. We see spiral galaxies, stellar nurseries burning in vibrant hues of ultraviolet, and superclusters of galaxies woven together like a cosmic web of light. But this is an optical illusion, a trick of exposure. The light is blinding, but it is infinitesimally rare. If you were to take all the matter in the universe, every star, every planet, every burning core of every black hole, and smear it evenly across the totality of space, the universe would not glow. It would be an absolute, unbroken black. The average density of the universe is roughly equivalent to a single atom of hydrogen occupying a volume of space the size of a cubic meter. The rest is the void. It is a desert of such incomprehensible vastness that the human mind simply lacks the neurological architecture to visualize it. We navigate our daily lives using a localized geometry. We measure distance in steps, in miles, in hours, driven down a highway. In the cosmos, these metrics collapse into absurdity. We must measure distance by the speed of light, a velocity so fast it can circle the Earth 7 times in a single second. Yet, even traveling at this absolute speed limit of reality, a beam of light leaving our sun takes over 4 years to reach the closest neighboring star. It takes 2.5 million years to reach the Andromeda Galaxy, our nearest major neighbor. And the space between here and Andromeda is not simply a vacuum, it is a profound thermal wasteland. To truly understand the mechanics of this wasteland, humanity had to build an eye capable of seeing the cold. We had to engineer a machine that could look past the blinding glare of the stars and peer directly into the frozen shadows of the universe. That machine is the James Webb Space Telescope. To observe the cold, the telescope itself had to become the cold. If a telescope is even slightly warmer than the freezing objects it is trying to observe, the microscopic vibrations of its own metal and mirrors will generate infrared radiation. It would be like trying to spot a firefly in the distance while shining a high-powered flashlight directly into your own eyes. The telescope would blind itself with the heat of its own existence. To prevent this, the engineers at NASA designed an apparatus of staggering complexity. They deployed a sun shield the size of a tennis court, constructed from 5 microscopic layers of a material called Kapton, coated in aluminum and doped silicon. This shield acts as a one-way thermal barrier. The side facing the sun, Earth, and the moon absorbs the brutal barrage of solar radiation, baking at temperatures near 110 degrees Celsius. But on the dark side of the shield, mere inches away, the temperature plummets into the abyss. The mirrors and instruments sit in a perpetual engineered shadow, chilling down to minus 233 degrees Celsius. But even this extreme refrigeration is not enough for the telescope's most sensitive instrument, the mid-infrared instrument, or MIRI. To capture the faintest whispers of heat from the deepest, oldest regions of the void, MIRI must operate at a temperature so low that the standard passive cooling of the sun shield fails. It requires an active cryocooler, a marvel of thermodynamic engineering that pumps helium gas through a complex labyrinth of pipes and compressors. This system forcefully strips the remaining kinetic energy from the instrument, driving its internal temperature down to a staggering negative 266 degrees Celsius. That is barely 7 degrees above absolute zero. It is only at this threshold of near absolute stillness that humanity can finally witness the true nature of the cosmic dark. And what we have found in that darkness defies all intuition. We have discovered that the universe is not just passively cold, cooling down like a forgotten cup of coffee. In certain regions, the universe is actively, violently refrigerating itself. Deep within the constellation of Centaurus, some 5,000 light-years from Earth, lies an expanding cloud of gas known as the Boomerang Nebula. When astronomers first pointed the Atacama Large Millimeter Array at this nebula, they expected to find the typical thermal signature of a dying star. What they found instead was an anomaly that broke the established thermal floor of the cosmos. The ambient temperature of the universe, the background echo of the Big Bang, sits at 2.7 degrees above absolute zero. But the core of the Boomerang Nebula registers at a mind-bending 1 degree above absolute zero. It is currently the coldest naturally occurring place known to exist in the entire universe. It is colder than the empty void of deep space itself. How can an object actively create a temperature colder than the surrounding vacuum? The answer lies in the violent mechanics of its own death. The Boomerang Nebula was once a star very much like our Sun. As it exhausted its nuclear fuel, its core collapsed, and the outer layers of the star were violently ejected into the vacuum. But in this specific case, the dying star is bleeding its mass at an astonishing, catastrophic rate. It is expelling gas outward at speeds exceeding 164 kilometers every single second. This creates a phenomenon known as macroscopic adiabatic expansion. Imagine a highly pressurized aerosol can. When you press the nozzle, the gas escapes and expands rapidly into the lower pressure of the room. As the gas expands, it is forced to do physical work against its own internal pressure, pushing its own molecules apart. This effort requires energy, and the only energy available is the internal kinetic heat of the gas itself. The gas sacrifices its heat to fuel its own expansion, causing the temperature of the can to plummet in your hand. The Boomerang Nebula is doing exactly this, but on a scale that beggars belief. The dying star is a ruptured cosmic aerosol can, blasting 100 trillion tons of gas into the void every second. The expansion is so violent, so impossibly rapid, that the gas is draining its own atomic vibration faster than the surrounding cosmic background radiation can warm it up. It is literally freezing itself to death through the sheer speed of its own explosion. It is a stunning paradox of astrophysics, an act of apocalyptic destruction creating an island of absolute thermal stillness. But the Boomerang Nebula is just a localized anomaly, a fleeting pocket of extreme cold created by a dying star. To truly comprehend the relentless hostility of the cosmos, we must look away from the stars altogether. We must look at the macro architecture of the universe. If you zoom out far enough, billions of light-years away from our local galactic neighborhood, the universe takes on the appearance of a vast three-dimensional sponge. The galaxies are not scattered randomly. Gravity, the silent architect of the cosmos, has pulled them together into massive, glowing filaments and walls. These structures stretch for hundreds of millions of light-years, forming a luminous web. But a sponge is not defined by its material. It is defined by its empty spaces. Between these massive filaments of galaxies lie the cosmic voids. These voids are the true masters of the universe. They make up roughly 80% of the entire volume of the cosmos, and the most terrifying of them all is the Boötes void. Discovered in 1981 by astronomer Robert Kirshner, the Boötes void is a spherical region of space measuring nearly 330 million light-years in diameter. To put that into a tangible perspective, if you were to travel at the speed of commercial jetliner, it would take you trillions upon trillions of years just to cross a fraction of its diameter. According to standard cosmological models, a region of space this large should contain at least 2,000 massive galaxies, each teeming with hundreds of billions of stars. But the Boötes void is empty. Extensive telescopic surveys have scoured this colossal expanse, peering deep into the darkness, searching for the telltale infrared glow of stellar nurseries or the X-ray emissions of supermassive black holes. They have found almost nothing. In a volume of space that should house thousands of galaxies, astronomers have identified a mere 60. They are lonely outposts, scattered so far apart that they are completely blind to one another. If the Milky Way galaxy were placed directly in the center of the Boötes void, the night sky on Earth would be a uniform, featureless black. We would not have known that other galaxies existed until the invention of deep space orbital telescopes in the late 20th century. Humanity would have believed that our single solitary galaxy was the entirety of creation. Standing in the center of the Botez void would be an experience of ultimate sensory deprivation. If you floated there, suspended in the middle of a 300 million light-year sphere of nothing, the concept of temperature would almost cease to have physical meaning. You are so profoundly isolated from any source of radiant energy that the photons from the distant walls of the void are stretched and exhausted by the time they reach you. There is no stellar wind. There is no galactic dust to absorb and re-emit heat. There is only the absolute inescapable baseline of the cosmic microwave background, whispering at 2.7 degrees above absolute zero. It is an ocean of thermal stagnation. Yet, this stagnation is not entirely peaceful. The universe is defined by extreme localized violence, surrounded by immense calm. Even as the vast majority of the cosmos slumbers in a deep freeze, the boundaries between the cold and the fire are zones of unimaginable physical trauma. Consider the supermassive black hole. They reside at the hearts of nearly all large galaxies, including our own. A black hole is, by definition, the ultimate thermodynamic sink. Its gravitational pull is so intense that the escape velocity exceeds the speed of light. Because heat is radiated as electromagnetic energy, as photons, and photons cannot escape the event horizon, a black hole emits no heat of its own. It is a region of space where temperature itself falls off the edge of physics. But the environment immediately surrounding the black hole is the most violent furnace in reality. When a star wanders too close to a supermassive black hole, it does not simply fall in. The tidal forces of gravity stretch and tear the star apart in a process known as spaghettification. The remains of the star are smeared out into a colossal, swirling disk of gas and plasma, known as an accretion disk. This disk is a maelstrom of friction. As the gas spirals inward toward the event horizon, it accelerates to an appreciable fraction of the speed of light. The sheer mechanical friction of quadrillions of tons of matter grinding against itself generates heat on a scale that makes a stellar core look like a candle. The temperature within the inner edge of an accretion disk can reach tens of millions, sometimes hundreds of millions of degrees. The atoms are stripped of their electrons, creating a turbulent, highly magnetized plasma that screams in the X-ray spectrum. The magnetic fields within this disk become tightly coiled, twisting and snapping under the extreme rotational stress. When these magnetic field lines rupture, they violently expel vast columns of matter outward into deep space at relativistic speeds. These astrophysical jets can pierce through galaxies, stretching for millions of light years. They are cosmic blowtorches of pure, highly energized plasma, plowing through the cold intergalactic medium. This creates a staggering juxtaposition. You have an object, the black hole, whose interior is locked away from the thermodynamic universe, surrounded by a razor-thin ring of matter burning at 100 million degrees. And just a few light years away from this raging inferno, the ambient temperature of space drops right back down to nearly absolute zero. The heat of the accretion disk is furious, blinding and absolute, but it is profoundly localized. The radiation it vomits into space travels outward, spreading thinner and thinner over the expanding surface area of a sphere. By the time the heat from that quasar reaches a dust grain floating in the outskirts of the galaxy, the energy has dissipated to a mere whisper. The fire is contained. The dark is infinite. The mechanics of this dissipation rely on the inverse square law. It is a simple, brutal geometric rule that dictates how energy weakens as it spreads through three-dimensional space. If you double the distance from a light source, the light does not become half as bright. It spreads over 4 times the area, dropping to a quarter of its original intensity. If you move 10 times further away, the energy drops to 1/100th. This mathematical law ensures that no matter how brightly a star burns, no matter how violently a black hole consumes matter, the resulting heat will rapidly dilute into insignificance against the sheer, overwhelming volume of the vacuum. We observe these violent phenomena from Earth and marvel at the energy of the cosmos. We see the supernova remnants, the glowing clouds of ionized gas, the dazzling arms of distant spirals. But we are looking at the exceptions. We are looking at a desperate losing battle. The universe is not a furnace. It is a freezer sparsely populated by a few dying embers. The heat is an anomaly, a temporary rebellion against the natural state of the cosmos. And as we dig deeper into the mathematics of how energy behaves at the furthest extremes of existence, we find that our understanding of thermodynamics begins to fracture. The rules that govern the fire and the ice start to break down, revealing a structural flaw in the very fabric of how we perceive reality. When we push the boundaries of thermodynamics to the absolute limit, seeking the purest, quietest corners of the cosmos, our foundational understanding of reality begins to fracture. The rules that govern the fire and the ice, the very laws of physics that allowed us to build cities and launch satellites, suddenly turn inward and collapse under their own weight. We have mapped the architecture of the void, measured the dying breath of the Big Bang, and chronicled the isolation of the galaxies. But when we look closely at the mathematical machinery running behind the darkness, we uncover a terrifying impasse. The universe, it seems, is hiding a profound structural contradiction. The crisis begins with the concept of absolute zero. In the classical world, temperature is a straightforward metric. It is the measure of movement. As an object cools, its atomic agitation slows. It stands to reason then that if you could continually drain the heat from a system, you would eventually reach a state of perfect, absolute stillness. This theoretical flaw is known as absolute zero, mathematically defined as negative 273.15 degrees Celsius. At this exact threshold, every atom, every electron, every subatomic particle should theoretically lock into place, frozen in permanent, immovable silence. It is the ultimate death of physics, a state where time itself, measured by the interaction of matter, ceases to have any functional meaning. For decades, the pursuit of absolute zero was seen as a difficult but mathematically sound engineering challenge. But as theoretical physics advanced into the 20th century, specifically with the birth of quantum mechanics, a disturbing realization swept through the scientific community. Absolute zero is not merely difficult to reach, it is physically, mathematically, and fundamentally forbidden by the universe. The barrier is not a lack of technology. The barrier is an ironclad law of reality, known as the Heisenberg uncertainty principle. Formulated by physicist Werner Heisenberg, this principle dictates that you cannot simultaneously know both the precise location and the precise momentum of a quantum particle. The more tightly you pin down an atom's exact position, the more violently uncertain its speed and direction become. It is a cosmic censorship mechanism. The universe flatly refuses to be perfectly measured. Translate this principle into the realm of temperature, and the implications are devastating. If a physical object were to actually reach absolute zero, its atoms would completely stop moving. Their momentum would be exactly zero, and because they are frozen in place, their location would be exactly known. This simultaneous perfection of knowledge is a direct violation of quantum mechanics. It breaks the foundational code of reality. To prevent this paradox, the universe enforces a mandatory minimum of chaos. As an object is cooled closer and closer to absolute zero, and its atoms attempt to settle into stillness, the uncertainty principle triggers a violent, invisible rebellion. The atoms begin to spontaneously vibrate. They shudder with a phantom kinetic energy that comes from nowhere. This is known as quantum jitter, or zero-point energy. You can strip away all the ambient heat. You can shield the matter from every star in the cosmos. But you cannot strip away this foundational anxiety of the vacuum. The matter will tremble purely because the mathematics of the universe demand that it cannot be still. It is like trying to pause a corrupted video file. The harder you try to freeze the frame, the more aggressively the pixels glitch and distort. This quantum jitter leads to the most catastrophic mathematical failure in the history of human thought. If atoms possess an inescapable baseline energy, then what about the empty vacuum of space itself? According to quantum field theory, the void between the stars is not empty. It is impossible for nothingness to truly exist. Instead, the vacuum is a roiling, chaotic ocean of virtual particles. These are pairs of matter and antimatter that violently tear themselves out of the fabric of space-time, exist for a fraction of a trillionth of a second, and then annihilate each other in microscopic flashes of energy. This is not a metaphor. It is a physical reality that has been experimentally proven through phenomena like the Casimir effect, where the pressure of these phantom particles can actually push two metal plates together in a vacuum. Empty space is boiling with quantum static, and because energy and mass are interchangeable, this means that the empty void has a baseline energy level. It has a weight, it has a temperature. When theoretical physicists sit down to calculate exactly how much energy must be locked inside this quantum vacuum, the mathematics produce an apocalyptic result. The equations suggest that a volume of empty space the size of a standard coffee cup should contain enough raw, latent vacuum energy to instantly boil all the oceans on Earth into plasma. The theoretical density of this energy is so immense that its gravitational weight should have caused the entire universe to instantly crush itself back into a microscopic singularity the moment after the Big Bang. Yet, when we look up at the night sky, the universe is not crushed. It is vast, expanding, and as our instruments tell us, profoundly freezing. The ambient temperature of the cosmos sits at a quiet 2.7 degrees above absolute zero. The discrepancy between the mathematical prediction of the vacuum's energy and the actual observed reality of the cold universe is not a minor rounding error. It is a mismatch by a factor of 1 followed by 120 zeros. It is a number so incomprehensibly massive that human language lacks a proper name for it. It represents the absolute breaking point of modern science. Our two most flawlessly tested frameworks of reality, general relativity, which governs the macroscopic gravity of stars and galaxies, and quantum mechanics, which governs the microscopic thermal jitter of atoms, are violently incompatible when asked to describe the nature of nothingness. They are speaking two entirely different languages, and both are claiming to be the absolute verified truth. We are floating in a universe that mathematically should be an unimaginable inferno of quantum energy, yet we are freezing to death in the dark. This paradox deepens into outright horror when we examine the most extreme objects in creation: black holes. A black hole is the ultimate triumph of gravity, a region where space-time is warped so severely that not even light can escape its grasp. According to the classical laws of thermodynamics and general relativity, a black hole should be the perfect refrigerator. Because it traps all electromagnetic radiation, it should emit zero heat. It should be an object of absolute perfect blackness, a thermodynamic dead zone existing completely outside the thermal economy of the universe. But in the 1970s, theoretical physicist Stephen Hawking applied the chaotic rules of quantum mechanics to the absolute darkness of the black hole, and he uncovered a mechanism that shattered our understanding of the void. Hawking realized that the boiling ocean of virtual particles in the quantum vacuum does not stop at the edge of a black hole. It happens everywhere, even precisely on the razor-thin boundary of the event horizon. Imagine a pair of these phantom particles popping into existence exactly on that threshold. Under normal circumstances, in deep space, they would instantly annihilate each other. But on the event horizon, the geometry of reality is torn. The gravitational tidal forces are so unimaginably extreme that the pair of particles is ripped apart before they can destroy each other. One particle is dragged kicking and screaming into the singularity, forever lost to the observable universe. But the other particle, pushed by the violent severing of its partner, is ejected outward into the cold vacuum of space. Because the universe demands that energy cannot be created from nothing, the escaping particle must draw its reality, its physical mass, from the black hole itself. The black hole pays the thermodynamic toll for the severed quantum pair. This means that the black hole is bleeding. It is radiating particles into the void. This phenomenon, known as Hawking radiation, dictates that black holes are not perfectly black. They glow. They emit a microscopic trickle of heat. And the mathematics governing this emission reveal a merciless, deeply counterintuitive truth. The temperature of a black hole is inversely proportional to its mass. The smaller the black hole, the hotter it burns. A supermassive black hole, billions of times the mass of our sun, is unimaginably cold. Its Hawking radiation is so weak, so stretched by its colossal gravity, that its temperature is fractions of a degree above absolute zero. It absorbs far more background heat from the cosmic microwave background than it emits. It is a frozen titan. But if you were to compress the mass of Mount Everest into a black hole the size of an atomic nucleus, the mathematics invert violently. A microscopic black hole would have a surface area so tightly curved that it would bleed its mass into the universe at an apocalyptic rate. It would glow with a temperature in the billions of degrees, radiating its energy away in a blinding cascade of gamma rays until it ultimately vanished in a thermonuclear detonation. Black holes evaporate. Given enough time, trillions upon trillions of years, long after the last star has burned out and the galaxies have ground to dust, even the most massive black holes will slowly boil away into the dark, converting their immense gravitational mass into a faint, dissipating mist of thermal radiation. This evaporation creates a theoretical catastrophe known as the information paradox, a dispute that currently paralyzes modern theoretical physics. In the framework of quantum mechanics, information is sacred. The physical blueprint of the universe, the exact quantum state of every particle, the arrangement of atoms in a star, the molecular structure of a dictionary, can be scrambled, but it can never be fundamentally destroyed. If you burn a book, the information is not gone. It is simply transformed into smoke, ash, and heat. With a supercomputer of infinite power, you could theoretically track every single atom of smoke and mathematically reconstruct the text. The universe keeps a perfect, unbreakable ledger of everything that has ever existed. But what happens when you throw that book into a black hole? According to general relativity, the book crosses the event horizon and is crushed into the singularity. The information is locked away, but it still exists inside the gravitational vault. However, Hawking's mathematics dictate that the black hole will eventually evaporate completely. It will slowly dissolve over eons, radiating away as random, chaotic heat. And when the black hole finally disappears, there is no vault left. The Hawking radiation that escapes is entirely featureless. It carries no imprint, no memory, no blueprint of the book, the stars, or the planets that the black hole consumed over its lifetime. If Hawking is right, then the black hole acts as a cosmic incinerator that permanently erases information from the universe. It deletes the fundamental code of reality. This is a direct, catastrophic violation of quantum mechanics. If information can be truly destroyed, then our entire mathematical foundation for predicting the behavior of the universe collapses. The past becomes mathematically unlinked from the future. The two pillars of human knowledge, the physics of the massive and the physics of the microscopic, are locked in a death match at the edge of the black hole, and physicists are terrified by the implications of either side winning. Yet, the universe possesses one final psychological cruelty regarding the nature of temperature, a phenomenon so bizarre it breaks the very concept of an objective reality. It forces us to realize that the freezing dark of the cosmos might simply be a matter of perspective. We assume that temperature is an environmental constant. If a room is cold, it is cold for everyone in it. If the vacuum of space sits at 2.7 degrees above absolute zero, we assume that is the objective, measurable truth of the void. But in 1976, a theoretical physicist named William Unruh mathematically proved that temperature is an illusion dependent entirely on how you move through space-time. This is known as the Unruh effect. Imagine an astronaut floating perfectly still in the deepest, darkest void between galaxy clusters. They deploy a highly sensitive thermometer. The thermometer interacts with the faint, dying echo of the Big Bang and registers a quiet, desolate 2.7 degrees. The void is practically frozen. Now imagine that astronaut ignites a hyper-advanced propulsion system. They do not just travel fast, they accelerate. They push harder and harder, their velocity compounding second by second, pressing their physical body relentlessly against the fabric of space-time. According to the Unruh effect, as the astronaut's acceleration increases, the quantum vacuum around them will begin to change. The empty space will no longer appear empty. The mathematical horizon created by their rapid acceleration will physically interact with the chaotic quantum jitter of the void. To the accelerating astronaut, the darkness will spontaneously fill with a glowing bath of thermal radiation. They will be bombarded by photons and particles that seemingly materialize out of nowhere. The harder the astronaut accelerates, the hotter the vacuum becomes. If they could accelerate at a rate approaching the speed of light, the ambient temperature of empty space would soar. The thermometer would read hundreds, then thousands, then millions of degrees. The void would become a raging thermonuclear furnace, capable of melting the spacecraft and incinerating the astronaut inside. But here is the paralyzing paradox. If a second astronaut were floating perfectly still, watching the first astronaut accelerate past them, the second astronaut would see nothing. They would see a ship moving rapidly through a freezing, totally dark vacuum. They would not measure any heat. They would not see any thermal radiation. The fire only exists for the observer who is accelerating. The heat is a localized relative phenomenon generated by the violent interaction between the observer's changing trajectory and the quantum static of nothingness. This means that cold and hot are not fundamental properties of the universe. They are relativistic experiences. The universe does not have a single true temperature. The freezing abyss of space is only freezing because we, on Earth, are drifting through it at a relatively gentle, unaccelerated pace. We are coasting. And because we are coasting, the universe presents itself as a thermodynamic graveyard. If temperature is an illusion, if information is being deleted in the dark, and if the mathematical framework of reality breaks down when we simply try to measure the cold, then we must ask what this means for the trajectory of existence itself. We are trapped in a system that is bleeding its heat away, governed by rules that we can barely comprehend, and hurtling toward a horizon that promises absolute stillness. If the universe is an engine, it is one running on an aggressively finite tank of fuel. The gradual bleeding of heat into the void is not merely a geographic cooling, a simple drop in temperature across the cosmic planes. It is the physical manifestation of time itself. In the strict, unyielding laws of thermodynamics, time does not flow forward because of some invisible metaphysical clock ticking in the background of reality. Time is driven by entropy. Entropy is the ironclad rule that all closed systems inevitably degrade from order to disorder, from concentrated useful energy to scattered, unusable noise. Imagine a pristine, tightly wound mechanical pocket watch. As the internal gears turn and the hands sweep across the face, friction generates a microscopic amount of heat, which radiates away into the surrounding air. The watch cannot run forever. Eventually, the mechanical tension in the mainspring is exhausted. The energy is entirely dissipated as low-level thermal static, and the hands freeze. The universe is that watch, but constructed on a scale of hundreds of billions of light years. Every time a star detonates in a supernova, every time a supermassive black hole swallows a wandering gas giant, every time you take a breath and your biology burns calories, localized energy is utilized and then scattered into the void as diffuse, useless infrared radiation. The fire of the cosmos is the mainspring unwinding. The freezing vacuum of space is the friction stealing that energy forever. Because this scattered heat can never be perfectly gathered back together. Because you cannot unburn a log of wood, unshatter a pane of glass, or command the warmth of a dying star to flow back into its core. The movement of heat dictates the absolute, unyielding arrow of time. We intuitively perceive the future as the direction in which we age, but fundamentally, the future is simply the direction in which the universe grows colder and more chaotic. Therefore, the freezing of space is not just an environmental hazard to be avoided. It is the ticking of the cosmic death knell. It is the inescapable mathematical proof that the reality we inhabit is terminal. This terminal trajectory forces humanity to violently re-evaluate its own existence. We look at our vibrant blue planet, teeming with sprawling biological architecture, deep oceans, and conscious minds capable of charting the distant quasars. Because we are surrounded by this richness, we assume that complexity, life, thought, structure, is a fundamental goal of the universe. It is not. Complexity is a fleeting, accidental byproduct of a thermal gradient. For anything remotely interesting to happen in the realm of physics, for carbon atoms to bond, for DNA to fold, for neurons to fire in the human brain, there must be a steep difference in temperature. There must be a concentrated hot source and a vast empty cold sink, allowing energy to cascade from one to the other, powering chemical engines along the way. Earth only sustains life because it acts as a fragile thermal bridge, catching the high-energy, high-quality fire of the sun. utilizing it to drive the weather and biology, and then venting the spent, degraded heat out into the frozen sink of deep space. We exist purely in the narrow, violent margin of this transaction. We are parasites feeding on a dying fire. But as the universe expands and the stars slowly, inevitably exhaust their nuclear fuel, these vital thermal gradients will flatten out. The hot sources will dim, and the cold sink of the void will absorb it all. We are currently living in what astrophysicists call the stelliferous era, the epoch of starlight. It feels permanent, eternal, and grounded to our human senses. But on the grand timeline of the cosmos, it is a microscopic flash. If you were to compress the entire lifespan of the universe into a single calendar year, the era of stars, the era of light, chemistry, gravity, and biology, would not even last for the first fraction of a single second on January 1st. The remainder of that cosmic year is a relentless descent into absolute unbroken twilight. We are a brief chemical anomaly, a spark of molecular friction generated in the early morning of a universe that is destined to spend the vast, overwhelming majority of its existence completely dead. To understand the weight of this future, we must look at what happens when the thermal economy finally collapses. Long after our own sun swells into a monstrous red giant, incinerating the inner solar system and boiling Earth's oceans into the void, it will shed its outer layers. What remains will collapse into a white dwarf. This is a dense, glowing ember of crushed carbon and oxygen, roughly the size of our current Earth, but holding half the mass of the original Sun. It will have no nuclear fire left to sustain it. It will rely entirely on residual heat, a cooling corpse slowly radiating its final reserve of energy into the dark. The cosmos will eventually be littered with these stellar remnants. Trillions of white dwarfs, rapidly spinning neutron stars, and silent black holes, adrift in an expanding, pitch-black ocean. This marks the dawn of the degenerate era. It is a time when the universe is defined no longer by shining galaxies and sweeping nebulae, but by locked, dead mass. It will take hundreds of billions of years, a stretch of time that makes the current age of the universe look like a brief preamble. But eventually, even these fiercely glowing white dwarfs will bleed out the very last of their warmth. Their atomic vibrations will slow to an agonizing crawl, and they will physically crystallize into black dwarfs. These are theoretical objects, structures of matter that have not yet had the time to form in our young universe. They are dark frozen spheres of degenerate matter, resting perilously close to absolute zero. They will be entirely invisible, emitting no light, no heat, and no radiation, drifting blindly through a void that has forgotten them. Occasionally, over time scales so vast they render human mathematics nearly useless, two of these unseen black dwarfs might blindly collide in the dark, generating a brief, pathetic flash of a supernova before the crushed remnants plunge right back into the freezing abyss. But even these rare, violent sparks of resurrected heat will eventually be extinguished by the architecture of the void itself. The expansion of space, driven by the mysterious, repulsive force known as dark energy, is accelerating. The distances between these dead, frozen husks will grow so incomprehensibly vast that gravity will no longer be able to bridge the gap. The universe will become entirely disconnected. An observer standing on the surface of a frozen black dwarf a trillion years from now would look up into a sky that is completely, flawlessly empty. There would be no neighboring stars. There would be no distant galaxies. The cosmic microwave background, the dying glow of the Big Bang, would be stretched so thin it would be entirely undetectable. There would be nothing but an endless, freezing black, a pocket universe of one, racing away from everything else in existence at faster than the speed of light. And yet, the degradation of reality continues beyond even this extreme isolation. The rules of entropy demand a final, uncompromising toll. In the deepest, most unfathomable stretches of time, reaching numbers like a 1 followed by 100 zeros, a Google of years, the very architecture of matter itself may begin to fail. Theoretical physics suggests that protons, the heavy, incredibly stable building blocks of all atomic nuclei, might not be immortal. Over unimaginable eons, the fundamental forces holding them together may weaken, and they may spontaneously decay, dissolving into lighter subatomic particles and faint, ghostly whispers of radiation. If proton decay is a reality, then the frozen black dwarfs, the dead planets, the cold dust of the cosmos, the very stages upon which the universe played out its history, will literally evaporate. The physical structure of reality will dissolve into a thin, featureless mist of solitary photons and leptons, drifting further and further apart. This slow dissolution leads to the ultimate thermodynamic fate of reality, a concept terrifyingly named the heat death of the universe. It is a profoundly misleading title. It does not mean the universe burns. It means that the universe has reached maximum inescapable entropy. All energy, all heat, all motion has been perfectly and evenly distributed across an infinitely large, infinitely expanding void. There are no hot spots left to provide energy. There are no cold spots left to receive it. Everything, everywhere, rests at an infinitesimal fraction of a degree above absolute zero. Because there are no temperature differences, no thermodynamic work can ever be done again. No energy can be exchanged. Nothing can happen. The universe will have finally achieved perfect, flawless equilibrium. It is a state where the concept of time itself becomes irrelevant, because time requires a sequence of events. It requires change, and in the heat death, change is mathematically impossible. The cosmos becomes a static, frozen monument to a fire that burned out long ago. The heat death is not a sudden, violent apocalypse. It is a meticulous erasure, a slow, agonizing bleed into a state of absolute nothingness. We are conditioned by our earthly biology to fear the fire. We fear the supernova, the catastrophic impact, the boiling heat of a dying sun. But the fire is merely a temporary symptom of a young, chaotic universe. It is the ice, the absolute unyielding stillness of the void, that will ultimately claim eternity. When we look up at the night sky tonight, we are looking at a fleeting, luminous illusion. We are witnessing the noisy, violent preamble to the universe's true, permanent state of being. The cosmos was not designed for life. It was not designed for light or beauty or meaning. It is a vast, cooling engine that accidentally generated a microscopic pocket of thermal friction, and within that friction, on a fragile speck of rock orbiting an unremarkable star, human consciousness briefly flickered into existence. We build colossal monuments of stone and steel. We engineer delicate machines to decode the behavior of black holes, and we hurl our radio signals into the dark, desperate to leave a permanent mark on the fabric of reality. We desperately want to believe that our ability to understand the universe somehow grants us a position of significance within it. But the thermodynamic laws that govern existence do not recognize our achievements. They do not care about human legacy, love, or suffering. The mathematical machinery of the void is entirely, flawlessly indifferent to the temporary arrangement of vibrating atoms we call civilization. Human consciousness itself is perhaps the most profound cruelty of this cosmic architecture. We are a collection of matter that has evolved just enough neurological complexity to wake up, look out into the infinite dark, and mathematically calculate our own absolute futility. We are a biological thermal anomaly, capable of comprehending its own inevitable freezing. Every thought you have ever had, every philosophical revelation, every ounce of existential terror you feel in the quiet hours of the night is nothing more than the temporary cascading of energy in a physical brain. A brain that will turn to dust on a planet that will be incinerated, in a universe that will eventually forget it ever contained a single spark of warmth. There is no grand finale to this story. There is no curtain call where the mysteries of existence are finally resolved for an awaiting audience. The strict trajectory of the cosmos promises only a quiet, absolute deletion. Try to imagine that final, unbroken era of the dark. The frozen black dwarfs have evaporated. The last rogue photons have been stretched so impossibly thin by the expansion of space that they simply cease to register as physical energy. The fabric of space-time continues to rush outward, pushing oceans of dead nothingness further away from other oceans of dead nothingness. There will be no light to illuminate the void. There will be no gravity to pull matter together. There will be no time, because there will be absolutely no physical events left to measure its passing. You are sitting right now in the narrowest, most mathematically improbable sliver of light, entirely surrounded by an abyss that is patiently waiting for the fire to burn out. The cold is not coming for us. The cold has always been the baseline of reality. We are just the brief dying embers falling through it.